Okay, so I'm just going to talk into our mission, my mission, at MA Building, is to be the leading passive home builder in Wanaka, influence in the industry, which is kind of where tonight came about. Not only by the homes we build, but also by enhanced understanding and adoption of passive house standards across the board. This mission is a grounded dedication to sustainability, health, and forward thinking in construction practices that challenge the status quo. That's our mission there. A little while ago, Amy, who's over here doing some great filming, and we went to Amy after a few conversations with some clients, potential clients, and they said, I don't know if you can build my house. And I've been pushing passive house so hard and massive big believer in the whole package, but they were coming to me with these houses that were just down a couple of notches from passive house. So we kind of created our little tier system to help people understand potentially what they can do instead of having to go potentially the whole hog. I mean, I know Jessica said, we'd like to go the whole hog. Unfortunately, at the moment, not everyone can get there. So I wanted to be able to help some people be able to get there with improvements. And I will put a little note there that the energy modelling is the key to that. We don't want to go and do things that we don't know how it's going to work and cause more problems like the house Jess talked about that started to overheat. So tier 1, low energy performance. This is probably what I would be calling, you might hear around the housing market, a high performance home. We still like to model it. We still like to test it with our air tightness, and we still like to talk about and think about the products we're using. I'll still try and get good windows in it, but it might just not have the critical detailing that, say, a passive house will. But it'll still get you, we find it gets you to sort of 60 to 70% energy reduction. The house we finished this year was relatively standard. It was airtight, it was ventilated, and we got that down from 180 kilowatts a square metre per annum. That's the use of energy, down to under 60. So pretty big reduction in energy use, and those clients are really, really happy since they moved in the middle of winter. Tier 2, this is actually a low, this is a passive house standard. So if people don't know, there's actually 3 standards passive house, low energy passive house, you got passive house, and then passive house plus. Slightly different tweaks to them and the levels that criteria that we have to meet. And then tier 3 is the fully certified passive house. We haven't got passive house plus on there at the moment. So how do we build our houses? I guess that's my role as the builder. We want continuous high levels of insulation, often double or triple the current New Zealand building code. We want to have thermal bridge-free construction. In other words, we work to limit the travel of cold and hot travelling through the exterior envelope of our building. We want high-performance windows. There's one out there sitting outside if you want to have a look at one. Often timber frames with triple glazing, shading, super important for overheating in our summers, and I'm living through that. I've got great examples of that. Solar again, we still need a heat source. That's something I want to break through. Like, houses still need a heat source, whether it's us, whether it's our ovens, whether it's our showers, whether it's our TVs, our computers, whatever it is. We need a heat source, right? One of the best heat sources is Big Yellow. Not too much, just enough. Modelling. Efficient hot water systems, good moisture management, which is what Kat was talking about with the vapor control barriers or the airtight papers. Good orientation, again, for that sun. Fresh air with heat recovery and air tightness. I'm not going to go through all 10 of them because we've only got a little bit of time, but we're going to focus on 7 of these examples. Insulation. Okay, so I've got there, speaking of continuous insulation, especially at the slab areas. So if we're using underfloor heating systems, which we find with tier 1 houses, we often can get rid of these. But if you're building a standard house and you've got underfloor insulation and you've got no slab and edge protection, we now have to have that here. But if you don't have it, a lot of the energy is disappearing out the side. Now I've seen photos where there's a frost outside and there's a thermal imagery camera and it's blue, and then maybe half a metre outside the slab edge is hot. It's red. Or there's frost and then the frost is melted. And you wonder where the energy is coming from? Straight out the side of your house. When you look at a wall, there are studies out there like the ladies before me talked about. The results found that often a wall that was supposed to be working at, say, an R4.2 would actually be working around an R2, which is some of the stats that Kat was talking about. So what do we do to get the insulation to work as best as it can? So we reduce our timber framing. I believe I reckon we're sort of down to 20 to 30% less than, say, most houses. Make sure a lot of our insulation and our ceilings go right to the outside walls, so it doesn't just stop here and then leave a cold void up on top. Wrapping and taping our exterior envelope to stop air movement through the wall, like a down jacket. You go and stand out in a cold, freezing cold southerly, in your down jacket, you still can feel that cold a little bit. You go and chuck your windproof jacket over the top, and then your insulation starts to work. It's pretty much the same as a house. We wrap it on the outside, we wrap it on the inside. We stop what we call wind washing coming through the insulation. Just allows that insulation to work really, really well. To work to the R rating that, I guess, from my point of view, you guys are paying for if you're a potential homeowner here. When we're all homeowners, whether a builder, an architect, or a potential someone that wants to build. The other one that always stuck with me from when Jess taught me passive house was, if in doubt, insulate out. So insulate on the outside if we can. And insulation also works across all seasons. So it does help to keep us warm in the winter, but it works in the summer too. So it does help to keep us cool in the summer. Why is it important? It allows the building to hold on to heat in the winter, keep the summer heat out. As I said, it allows exterior surfaces to stay warm continuously, allows insulation to work as close to the R rating that's on the bag. Thermal bridges. A little bit of what Jessica was talking into is modelling the detailing. So around windows, around our floors, where the slab meets the wall, the roof junctions, anything that travels in and out of the house, we try and avoid this, but they'll model it. But that thermal bridge is a smooth stopping the cold traveling between the internal and external environment, like a free highway for the heat that you have paid for via one of the heating systems we use in New Zealand to leave your building. So just let that land a little bit. So you paid for heating, and it's all going out your walls. For me, that's not really ideal. So how do we build without thermal bridges? Again, we fully insulate our slabs. Fully insulate means under the concrete and up the edge. A little bit like Jessica's model earlier. That was actually a really interesting aspect of building that house, because I've seen Jessica talk about that particular detail a few times, and I was quite blown away by just adding a little strip of insulation, the polystyrene, different polystyrene, the impact it had. It was quite incredible. If we need steel for structural elements, often we do here in Wanaka, we want the big, vast views and things like that. We want to bring it inside our thermal insulation. We don't want it on that cold getting to our steel. Steel is one of the worst conductors we can get. Reducing our timber framing creates less contact from inside to outside. In winter, you may have noticed when walking around the streets first thing in the morning that some houses you see have squares. What that is the insulation working, keeping the outside surface cold, doing its job, and where it's melted, or the lines, that's your thermal bridge. That's the warmth that's gone through the wall, melted the outside face, and you get the squares. Why is the thermal bridge important? It stops you losing your heat you've paid for. Stops the cold draft feeling, so it stops you having that feeling when you're sitting in your house up against, say, a surface or a particular detail that you guys probably don't, if you might not even know it's in there, but it might be a big steel beam or steel column or something in there, and the cold's traveling through it, and you kind of just get that cold and stop the cold spots. So often up and down the coastlines especially, a lot of houses will get mould in the internal corners of south-facing bedrooms especially. Thermal bridging doesn't help with that. Number 3, air tightness. Now, this is relatively new to New Zealand, but it has been used worldwide for many, many years. Also known as vapour control barriers, which is looking after our external envelopes. If we don't lose it, as I say, if we don't lose the air, we don't have to reheat it. So I'll say that again. If you don't lose the air you've heated inside your house, you don't have to reheat your air. The less of the warm air you lose through your building, the less of the air has to be reheated. Yet we Kiwis love a fire, as I do. I love a fire. But when we're thinking about how a fire works, it needs air to combust. Where does this air come from? It needs to draw it from somewhere. Yes, it's drawing it from inside your house, but also it's drawing it from outside. So it pulls cold, freezing air at times through gaps, open vents, poor windows into your house. So let's say that again. It pulls cold air from outside, and then we have to heat that air. So we have to what heat, cold air from outside that doesn't sound, I'm just going to say it instead of my notes. So you're pulling in cold air into your house to heat your house. That just to me sounds a little bit backwards. You're paying for your firewood, you're paying for your heating systems, you're paying for whatever. And once this stuff starts to work into my brain, it just becomes so obvious. But when we lose a vapor control barrier or an airtight membrane, we don't lose our heat and instead retain the heat that we have already created in the building from oven, showers, sun, body heat. We don't need as much heating. So we don't lose it, we don't reheat it. When we speak about measuring air tightness, we use air changes per hour. So our house is always losing air. A new standard house, like the lady said, 4 to 6 times an hour. Older houses, even more. Whereas a passive house has to get to 0.6 air changes an hour. So I'm going to throw some numbers at you. So if we had a house with, say, 1,000 cubic meters of air, a non-airtight house is then losing 4,000 to 6,000 cubic meters of air every hour. If you want to times that by 24, go ahead. A passive house would be around 600 cubic meters of air an hour. The passive house we built with Jessica, we achieved a 0.32 air tightness test. So that is only changing 320 cubic meters of air an hour. So we talk about a standard house that most of us, not so much me anymore, but a lot of getting built. You're somewhere between 4,000 and 6,000 cubic meters of air. The passive house we did was 320 cubic meters of air. So it's a massive, massive difference. How do we achieve this and what's different for a builder? I want to talk to builders especially. We use the Pro Clima Tapes and members, and there's others out there. It's a team effort. All have to be on board, trades included. It's a true test of our skill set. And when we get our buildings pressure tested, so that's one thing I really, really love. As builders, we don't really get our houses tested. Council comes along, we've got one of the best in the back there. Tick, 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 yeah, you've done that, you've done that, you've done that. But apart from that, we don't get any other tests. But when we get a pressure test done, we do. And we go around the house and we try and find the leaks. And it's really, really incredible how a teeny tiny little pinhole that just a little bit of tape can fix is just sucking through. So we use a couple of different ways, but we use incense. So we go around with incense sticks and you put it up against the windows and you see the air coming in. It's quite phenomenal. It's really, really fun. It's a good challenge. There's more planning involved, so thinking ahead. So adding sewer papers into certain areas, getting the sequencing right, working with the trades, the sparkies, the plumbers at different times. I'm always looking at ways to install the air barrier as efficiently as possible as well, and that's a cost thing. We're trying to make it efficient, make it cost efficient, but also get it to the highest standard as we can. It allows an extra layer of insulation installed horizontally, which in turn helps with that thermal bridging. So there's some models outside that you can have a look at that sort of describes that a little bit more. Why is it important? It helps keep moisture from entering the external structure, allowing insulation to work better and stop potential mold. Like the ladies were saying, if we get moisture into our wall cavities, there is a dew point in there. Not all of it will turn to water, but some will. There's more comfort, there's low drafts, there's less heating required. And to finish, to put a nail into the coffin in New Zealand, who think that an airtight home can't open their doors and windows, this is 100% untrue. You can open anything you want, any time of the year, whenever you want to. What I say to that, though, is if it's 30 degrees outside or 33 degrees outside, go ahead, open your windows up, and your house will be 33 degrees inside. If you want your house to stay 24, 23, 25 inside and be comfortable, keep your high-performance windows shut. Come on. For windows. Why high-performance windows so important? So when we look at a wall, I was telling some people out here before, we're looking at a wall needing to be about an R4. We're back to our R ratings again. And when we look at a window to the current building code, it's R.5. So it's, excuse my language, piss weak compared to a wall. When we're looking at a really, really good window, you might get up to 1.3. Is that about right, Jessica? 1.3, 1.5. A really, really good window. So we can now see how poor and important they are to choose right and install right. Without them, we cannot use the sun to heat our houses. There are wins and losses, and the modelling is really, really important. So they'll model the wins and losses, and Jessica informed me on my wins and losses, and I get lots of wins, too many. How is it different for a passive house? We install them in the building line, which is what Kat was talking about. We measure a window in parts. So we look at the frame, we look at the glass, then we look at it as a whole, whereas the code just looks at the window as an R5. They don't look at the glass, they look at the frame, they just look at the whole unit. So that Jessica and the team will actually split it right up. If we go into fourth form conductivity science chart, we see aluminium, PVC, timber. They have a very big difference, with aluminium being the most conductive of all, allowing hot and cold to travel so easily. This is why we get so much condensation, even on new thermally broken aluminium windows, plus where they're installed, as they just can't keep the cold at bay well enough. We tape the inside and outsides. So when we fit them, we tape the outside, which is something a bit different, which actually really helps with the watertight exterior as well. So it just helps that moisture. You won't feel cold sitting up against the triple glazed window. So when you're back to that sort of full form science again, when you're sitting up against an aluminium thing, you'll feel cold, whereas up against one of these timber windows, you don't feel that cold. Like I said to someone before, glass is glass, or is it? There are so many different options when it comes to glass, not just double or triple glazing. Using the model, we can actually determine the most fit for purpose glass per house and the location. So you can actually go, well, that's all north facing, well, we need to do this, and that's south facing, we need to do this. You can actually pick at all your windows as well. But they're really, really, really important. Just going to the cost on the window a little bit. So they are going to cost you more. With the model, we can help to, I guess, determine where you want to spend your money. It's a big part of my role, big part of my job, big part of being a high-performance builder is helping clients make the right decisions along the journey to get the best house for their money, and whether the windows are the best pick. But a really, really good performance window, like a really, really good performance car, is going to cost you more. Air circulation, which we talked about with ventilation before. So when we build an airtight home, we have to ventilate it. Otherwise it sweats. It just wouldn't work. The heat so we call it a mechanical ventilation with heat recovery. The heat recovery part is the most important, and how the system works and how it is different to, say, I'll label it an HRV system, because I think most people will understand what I'm talking about. So MVHRs, or mechanical ventilation, they pull warm air from bathrooms, kitchens, where the air is warm and damp, and returns the air to the main unit and then extracts it outside. It then has a return air duct, which brings fresh air back into the house and delivers it to the living room, bedrooms. But unlike an HRV system, this is where these systems excel. As the cold, fresh air comes in, it retains up to usually around 90% of the air going out. So say a room's 22 degrees, then the return air is coming back in. Whereas, say, a fresh air system, I'll call it a fresh air system, is just bringing in cold, fresh air. Sometimes that air could be -5, -6, -7, -8. So we're back to that whole, you're bringing in cold air again, then you got to pay to reheat the bloody stuff again. I think the pennies are starting to drop potentially now. So how is it different for a builder? More planning, definitely. More planning for the designers as well. So we need to create space for the system and the pipes and the ducts to all run, and working in with another trade. So I jump in often at the start of a build while it's getting designed and really work hard with my fresh air guy and the designer to get the system to work. Why is it important? Keeps the house fresh, keeps the house dry, reduces the energy demands, costs the same as about a light bulb to run, so it's negligible things there. And it is required with an airtight house, but still can be used in a non-airtight house, like Vicky was saying with the central lakes. So they're not building airtight houses, but they're still putting MVHRs in. Shading. This is quite a new topic that Amy and I have been talking into quite a lot. And another architect actually, Ray McLean, said this to me. It's quite easy to keep a house warm, but to keep it cool is actually more challenging in our environment a lot of the time. We all know the stories of how cold some of our residents in Central Otago get, but in the summer, when the summer hits, we get the stories of 30-degree houses and being able to sleep. Me being one of them, Amy being another. How does this happen? Poor planning and design. We've moved a lot of the eaves on our houses that we used to have not that really long ago. And we use a lot more glass than we used to. We then face a lot of that glass to the north and northwest, especially in Wanaka, because the views are unreal. As that west setting sun comes through Wanaka, it just gets lower and lower and lower and lower and lower, and it gets hotter and hotter and hotter and hotter. And then that's what causes a lot of our overheating in the late afternoon. So how can we combat this? We can model it. To see if we have a problem and how big the problem is. Shading, whether that is via eaves, without horizontal shading, like blinds, or depending on the location of the window. So if it's a west-facing window, you might need vertical. If it's a north-facing window, you might get away with an eave. Stopping the sun from hitting the glass. Now, this is a real key point. I hear a lot of the time, I've got blinds on the inside of the window, so it's, stops the heat. Doesn't quite work like that. If the heat gets that glass, it's through the glass, it just traps in behind you. It's still inside the envelope. So we've got to stop it out there. You've got to shade, you've got to use trees, you've got to do all sorts of things. But you can't let it hit that glass. Lost notes now. Back to our windows. Being gains and losses. In winter, we want that precious sun's warmth. So using some shading or designing items that can be multi-purpose is super important. So that house that Jessica had up at Callagher Drive, we ended up getting some mechanical blinds that sat on top of her pergola so she could shut them in the summer. That client was here this summer, and with use of opening doors in the morning, use of the blinds, she was able to keep her house under 25 degrees all summer long, and I don't think she turned the heat pump on to cool, which is quite incredible, especially for a passive house because you've got all that insulation and all that glass like Jessica was talking about. Last but not least, I think I've almost stuck to time orientation and form. Again, really, really important aspect of how a house may or may not work. Again, back to those wins and losses. If a house faces north-south, they may not get enough sun in winter, but then too much in summer. So I'm looking at a house at the moment, they've got a whole 2-story, low-story bank of west-facing windows. Now, we know they're going to get heaps of sun in the summer, so we know we're going to have to shade. But I hit them with a question just 2 or 3 weeks ago. They were umming and ahhing about the energy modelling. I said, you might not get enough gains in the summer because they don't have enough sort of east and north windows. So that was a bit of a light bulb for me as I'm going through my journey to go, well, actually, we need to model everything. So if it faces south, you might not get enough, but then if it has too much west, you're going to get too much. So the form can determine how well a building will work and also how easy it may be to achieve a low-energy home. Like Jessica talked about, that Callagher Drive build, quite good with the north-facing windows. If it was facing all south, it was going to be almost 3 times as hard to do, right? It meant there was 3 times the amount of everything, but it would have just been a little bit more tricky. So we like to be involved to a point, not to change the design totally, but to add some notes, ask some critical questions around performance when it comes to designing a high-performing home. So yeah, back to those tiers, just to finish. I'm an open book, not a finished book, that's for sure. I'm still learning so much as I go. All these events that we have and I show up to and I talk to builders and I go to other houses and guys are doing some amazing stuff. And like I said, back to the start, it's a bit of a goal of mine to help our industry all just come up together. It's not so I can have the whole lot, so we can all inform and the rising tide saying, so we can all come up to bring our houses up. It's so our future generations don't grow up in, like Kat was saying, houses that we grew up in. So they grow up in a good house, and then they want to build a house or whatever. Then their expectation comes up. So then eventually, over the next few generations, hopefully we can start to learn from the world. I actually got asked a question just to finish last week in a Q&A. And I really wish I'd answered it like this. It's about government and if they should get involved. I said, I want government to get involved. They need to be involved. I just want them to start to maybe listen to some of the experts, like Jessica and her team, Oculus and their team, start to listen to some worldwide countries that are making changes, that have been doing this for a very, very long time. Yet we try and rewrite our own script all the time. We want to come up with our own way. There's a way. You're looking at it. It's been getting done for 30 or 40 years all around the world. I hope that in time we build more of them, hopefully the costs will come down a little bit with it. There are more costs. There are more involved. We can't build a house with more things in them for the same price than the one down the road. But it's where you want to spend your money, whether it's on the views and the beautiful kitchens, or if it's in a comfortable, really efficient home that will save you money for many, many years. So yeah, I'm going to finish on that. We're going to do a quick Q&A. However many questions there may or may not be. And we'll just roll straight into it, I think, because it's just on how to say it now.